Greetings, everybody. Learning as a hobby here. I want to do my problem of the day for you guys. So let me bring up the whiteboard and I'll show you what it is and then we'll prove it. Okay, so this is a pretty famous formula that I'm going to show you guys. I want to derive a formula for generating Pythagorean triples for you. But before I do that, in case you don't know what a Pythagorean triple is, let me explain what that means. And then I'm going to prove an interesting lemma and then use that to prove to show that we get a formula using that lemma. So first, let's start with a definition. So a Pythagorean triple is a three-tuple of positive integers that satisfy the Diophantine equation x squared plus y squared equals z squared. So that's what we mean by a Pythagorean triple. You can also talk about this in terms of um, the Pythagorean theorem, which is why it's called a Pythagorean triple. So geometrically, x, y, z represent the three legs of a right triangle, where z is the hypotenuse. And famously, the Pythagoras tells us that for any right triangle, so this is a right angle here, meaning 90 degrees, then if the legs here are x and y, and the hypotenuse has length z, then we know that x squared plus y squared is equal to z squared. I'm not going to prove that theorem here. If you'd like me to, let me know down in the comments, and I'll gladly prove the Pythagorean theorem for you guys. But I just want to tell you what it says today. Okay, so that's what a Pythagorean triple is. It's a positive integer three tuple of three positive integers that you can think of as being legs of a right triangle, where the third integer is the hypotenuse. Okay, and by the Pythagorean theorem, they always satisfy the Diophantine equation. Okay, so let me give you a lemma, and we'll use the lemma to prove, or to derive rather, the formula. Whoops, why did that happen? Lemma. Wait, let n be a, actually, yeah, I'll do natural numbers. Let n be a natural number. Then if you add up the sum of the first n odd natural numbers, you always get n squared. So let's prove this real quick. You can prove this easily by using an inductive argument. And then I want to use this to derive a formula for the Pythagorean triples. All right, so here's the proof by induction on n. So induct on n. All right, this will be some good review for induction proofs. So we start with our base step, which will be n equals 1. And clearly 1 is equal to 1 squared. So the base step is satisfied. Now we can move on to the inductive step. And remember, the inductive step always starts with the inductive hypothesis. So assume the sum j going from 1 to n of 2j minus 1 equals n squared for some natural number n. And then we show that the formula works for n plus 1 as well. So consider the sum j going from 1 to n plus 1 of 2j minus 1. Now, again, I'm not going to assume that that's equal to n plus 1 squared. I have to show that it is, right? You can't assume it because then that's circular reasoning. But let's show that under the hypothesis, under the inductive hypothesis, then the formula still works for n plus 1. All right, so this is equal to the sum 2j minus 1, j equal 1 to n, plus 2 times n plus 1 minus 1. And I can simplify that expression. The sum of 2j minus 1, j going from 1 to n by the inductive hypothesis is just n squared, right? And then if I simplify the 2n plus 1, so distribute the 2 in other words, and then 2 times 1 is 2, minus 1 is 1, so plus 1. Notice that that's a perfect square trinomial. It factors into n plus 1 squared, right? So that means the inductive step is satisfied. So the formula here holds for all natural numbers n by mathematical induction. Okay, so now that we have this lemma, let's use that to derive a formula for the Pythagorean triples. Okay, so um, take uh, take n plus 1 large enough so that um, 2n plus 1 is a perfect square. Or maybe I should say it doesn't necessarily have to be large, but take n plus 1, I'll just say maybe farther down the sequence of odd integers or odd natural numbers, enough so that 2n plus 1 is a perfect square. So in other words, what we get is 1 plus 3 plus all the way up to 2n minus 1 plus 2n plus 1. We know that that's n plus 1 squared by what we just showed by the lemma. But also, we know that this is n squared. This is n squared plus 2n plus 1 equals n plus 1 squared. All right, and now we're assuming that we went far enough out into the sequence of odd integers such that 2n plus 1 is a perfect square. So we'll say assume m squared equals 2n plus 1, and then I can solve for n. So n will be m squared minus 1 over 2, and I can replace n with m squared minus 1 in the formula that I have up above. So in other words, n squared plus 2n plus 1 equals n plus 1 squared becomes m squared minus 1 over 2 squared plus m squared equals m squared minus 1 over 2 plus 1 squared. Let me just fix that. All right, and then I can simplify this. So this gives me m squared minus 1 squared over 4 plus m squared equals, here if you put this over the LCD, maybe I won't skip steps just in case people get confused. This is m squared minus 1 plus 2 squared all over 4. And if you simplify that, that's m squared plus 1 squared over 4. And I can multiply through by 4. So I'll just say multiply by 4. And that gives us the equation m squared minus 1 squared plus 4m squared equals m squared plus 1 squared. Okay, and then lastly, I can bring that 4 inside the square, right? 4 is 2 squared. So this is the same thing as m squared minus 1 squared plus 2m all squared equals m squared plus 1 squared. And this gives us a formula for generating Pythagorean triples. So for example, let's say we choose m equal to 2, let's say. Then if I plug that in, I get 4 minus 1 squared plus 4 squared equals 4 plus 1 is 5 squared, or in other words, 3 squared plus 4 squared equals 5 squared. 3, 4, 5 is a, you know, usually one of the Pythagorean triples that people remember from high school geometry. So we get that one from choosing m equals 2, but you can choose m to be any number that makes the number m squared minus 1 positive, and then you'll get as long as you choose m to be a natural number that's makes m squared minus 1 positive, then you get a Pythagorean triple. Okay, now this is not the most general form that you can derive of this. Notice that, let me just say this down here as a note, x squared plus y squared equals z squared is invariant under scaling, right? Meaning that if I take uh, all the variables to be some positive natural number times the original quantity, it doesn't actually, it still satisfies the equation. So for example, replace uh, x with alpha x, y with alpha y, z with alpha z. Maybe I'll call this x hat, y hat, z hat, alpha z, where x, y, z is a Pythagorean triple. And alpha is a natural number. Okay, then if we look at alpha x squared plus alpha y squared, this is equal to alpha squared x squared plus alpha squared y squared, which is alpha squared times x squared plus y squared, which is alpha squared times z squared, because x, y, z are Pythagorean triples, right? And notice that n is not 0, so you can divide out by the alpha squared, and this equation is obviously satisfied. So if x, y, z solves x squared plus y squared equals z squared, then so does alpha x squared plus, whoops, alpha y squared. Sorry, square should be on the outside of the parentheses, plus alpha z squared, where alpha is a natural number. Okay, so that gives us the general formula for generating Pythagorean triples. So we can take x to equal alpha times m squared minus 1. We could take y to be, what was it, 2 alpha m, I think, right? Yeah, 2 alpha m. And we can take z to be alpha times m squared plus 1, where alpha is a natural number and m is a natural number, m greater than 1. Right. So that gives you a way of generating uh, the Pythagorean triples. Okay, so let me stop here. All right, let me know what you guys think down below. I hope you're enjoying, again, these problems of the day. I think for what I'm going to do for tomorrow is I'm going to generate the same formula for generating Pythagorean triples, but I'm going to do it through a different method. I kind of enjoyed doing the problem of the day yesterday where I did the same problem through different techniques. So I think tomorrow that's what I'm going to do, and you guys can tell me which one you like best. All right, I'll see you guys tomorrow. Like I said, let me know down what you think down below. Give me a like and subscribe if you enjoy the content, and I'll see you guys in the next one.